science. And he's also been director of Deep Reinforcement Learning Center at Tencent AI and has been a faculty member at Princeton University and Johns Hopkins. He got his PhD in machine learning and statistics at Carnegie Mellon, where he was advised by John Lafferty and Larry Wasserman. He's received many awards, including a Sloan Fellowship, the IMS Tweedy New Researcher, the ASA Another Young Scholar Award, and NSF Career Award, and on and on. And we're very fortunate to have him here today to talk about human-aware robots and his use of advanced systems design in order to do experiments with them.
Okay. Okay, thanks a lot, Dave. So, and yeah, it's a great pleasure to be here. So today I'm going to introduce human-aware robots, but mainly from a system perspective. So because this is a lecture, so in this lecture I'm hoping to deliver several concepts. One is about a scientific framework for developing robots. That's what I call simulational inference. That's the first thing. And then after that, I want to also explain what are the underlying IT infrastructure are supporting this type of simulational inference and doing the computation. So that's the second part. We want to learn a little bit about cloud computing. And then after that, I want to showcase some preliminary results we have been working on about robotics, the applications, and to showcase how these systems are actually working together. And then if we have time, I would like to explain a little bit more about the possible extensions of this stuff. Yeah. Okay, so then let's start. Oh, sorry, I need to. So this is based on the joint work with my students at the Magics Lab. Dave just explained the meaning of Magics Lab. So then the major part of the system part in this talk is mainly collaborated with Jia Wang. She is a master student at Northwestern Computer Science and did all the heavy lifting on the computer system part. That's correct. Yeah, this is one of the tallest buildings in Chicago. Yeah, so that's I think it's 1,400 feet. Yeah, so that's a very nice place to visit. Yeah, and then the robots part, I actually worked with Qingjie and Guo. These are the robotics person. These are the three major student collaborator for this topic. So, what is human-aware robots? Yeah? So they are essentially just robots that can interact with human and assist human. Yeah? So they could be embodied as hardware robots, like a mobile luggage. Then in the airport, this luggage is following people. Yeah? That's one type of robots, human-aware. But they don't have to be really physical. Yeah? Sometimes they could be even software bots, like a preventive health system. Then the people use a certain IoT device, like the watch and then the cell phone app or pads. Yeah? So then they can also collect certain human parameters, human body parameters, upload them into the cloud, then they do some analysis in the cloud, and then doing the backward intervention to human. Yeah? So this is also a type of robots and human-aware software bots. Yeah? So then but robot research has already been there for more than half a century. What is special about this human-aware robots? Yeah? So because this type of robots need to interact with human, deal with humans. So then we want this type of bots to have stronger skills in terms of vision skill, like perception and decision and conversation. Yeah? So we want the robots see better things. Yeah? We want the robots can make decisions in subtler situation compared to the traditional industrial bots. And we also hope these robots can communicate with human in the more natural channel, like natural language. Yeah? So these are the special parts of human-aware robots. But then from the mathematically, so this type of robots, we could always, give me a minute. I think the Stanford network keeps showing up. I will turn it off. Okay. So mathematically, we could always formulate this type of human-aware robots problem as a sequential decision problem. Here, the robot itself is a software agent. It can perceive from an environment with possible human involvement. Then after the robot sees this environment, and then they generate certain internal states, and then they try to generate some understanding, then they make the decision to do intervention with the environment. And this process keep going on and on. So this is just a classical Markov decision process formulation of the robots here. So then after introduced what is human-aware robots, so here are the major topics of today's lecture. So I mainly want to deliver like 3 topics. So first, I want to introduce you a scientific framework for developing robots, which I gave a name called simulational inference. So I will make this a little bit clearer. So this is a more like a generic framework. And within this framework, we can formulate the robotic, the learning or development problem as a massive computational experiments here. And then how shall we conduct this type of experiments? Because robot is very special. It's not just software, it also involves hardware, and there are a lot of very heterogeneous resources. So that's where we need a more sophisticated cloud system infrastructure than to support all these things. And I would like to explain a little bit more about the underlying logic of this cloud system. So then how they are organized together, why we need all these different components here. So that's the second thing. Then after that, I want to introduce you 2 pilot studies, 2 examples about some projects we have been working on, and to showcase how these things work together. Then if we have time, we'd like to explain a little bit more about possible extensions of this whole thing. Okay, so now it's the first part. I want to introduce you this simulational inference framework. So essentially, simulational inference framework has 2 major ideas. The first idea is just called simulation. So simulation idea is because we are dealing with robots, and robots most of the time in the physical world, so then they can generate data by interacting with human or just doing operations. So this is the physical robots. But then when we are developing these robots, right now in the current robotic industry, the most popular approach is we always want to create a digital twin of this physical bot. That's called a simulator bot, simulated robots. So we see the simulator is much cruder compared to the real physical bot. But the good thing for simulator is it's fully configurable. We can just manipulate simulator whichever way we want. It's super cheap. And also, for this simulator space, so you see simulator is more like a generator. It could generate data. Then here I put a prime here. Then from a model family, parameterize family. And we can parameterize this. Then there leaves some space for potential learning or inference or adaptation. But then when we really want to deploy such bots, how shall we do that? So then the one thing we need to do is we want to, based on the real data, to calibrate this simulator, this parameter theta. This is a little bit like learning. But then this type of adaptation is more like from the scientific perspective, it's more like doing induction, because underlying simulator is a generative model. It's more like a law or a way to understand the physical world. So it might be wrong, but then we want to just find the best we can by doing this step here. But assuming we do have a simulator, then we could further explore this simulator, to generate more data, do this is what I call deduction, trying to utilize the simulator, deploy the better robots in the real world. And this whole process could be iterative, we keep doing this. This is more like a very overly simplified the scenario or paradigm for the scientific developments here. We need to do this induction, deduction, keep doing iterations. So then this is the simulation idea. But there is one tricky part here, because you see that in general for robot simulator, this G theta, it's different from the simple statistical model or something that we can get an explicit form. In general, it's a bunch of algorithms. It's complicated enough. They are interacting with each other, and there are a lot of components here. So then what we can is we can generate data, but it's not easy to get a mathematical formula. So it's not that straightforward to directly fit these simulators into the data. So how shall we bridge this gap here? That comes the second idea called the neuralization idea. So this is just like in the current deep learning literature. What people do is utilize a neural network, this function fw, w is a parameter, as a universal function approximator. Then they're trying to just memorize whatever we have seen. So encode them into the parameter w. So then they're combined together, simulation and the neuralization. So then here I gave a little bit formulation about the simulational inference problem. So you see, this problem, we can formulate it as a bi-level optimization. Yeah. So if we look at the internal level first, so here, for each simulator G, then it has a parameter theta. Then the G theta, we could use it to generate a lot of data than the data prime. Yeah. So then first generate a lot of data using this the simulators. And then we can use whichever fit function to fit a neural network here. For example, here could be supervised learning, could be reinforcement learning. Just whichever type of learning methods we have, then we can fit this the neural network to this to the generated data. Then this one you can use whichever one you care about. For example, if you want to train a robot has the very best policy, then you can use the cumulative rewards then for the reinforcement learning setting. But if you just care about getting the very accurate prediction system, like doing the image classification, then you can use the cross-entropy loss. Yeah. So this is a very generic framework here. So, but my point is, you see here, this W is indexed by the parameter theta. So it's really being parameterized by this theta. And in fact, in many deep learning problems, we make the training error to be 0. This is just like we are utilizing this W to memorize this whole, whatever has been generated. So then once we get this W theta, we can go to the upper layer. So in the upper layer, we can have another fit function that could or could be different from this inner one. And then yes?
So would it be accurate to say, like, in a traditional situation,
yeah,
you could have a linear model, and down here something like Gaussian data?
That's exactly correct, yeah.
Parameters, and then up the top, you might have non-Gaussian data, but you have a variety of linear models that you're going to sweep through until you find the one that comes out, and then you take the slope of that model as your reported theta hat. So in that special case, it corresponds to something that we know.
Yes, that's right, yeah. That's correct. Yeah.
You've got a much more general situation where presumably this includes, like, it's reinforcement learning.
That's exactly correct, yeah.
Over policies.
That's right, yeah.
Yeah.
Yes. So this one in the very simplified setting, then this is just a bi-level optimization problem, and people has already studied this before. But what is newer here is for the robotic applications, yeah, a lot of modern algorithms, then they are using like the reinforcement learning type stuff, and then they are using the neural network as a functional approximator. So I want to explicitly emphasize on this part, because later this will affect how do we design the algorithm and doing the analysis for this framework here. Yeah, but that will not be the focus for today's lecture. But I want to give you a little bit more, the extra information here, because for solving this problem, there are many ways to solve it. For example, depending on whether this W is differentiable with respect to theta or not, and it depends on this G theta. Theta is a discrete or continuous parameter, and G is differentiable with theta or not. Then there could be different type of algorithm, and also depends on the dimensionality of theta, how high or low it is. Yeah. So for example, a trivial method to solve this whole bi-level optimization, if theta is in low dimensional space, then we can use the Bayes optimization. Yeah. So that's essentially use Gaussian processes to model this, observe the objective function. And then there are certain uncertainty quantification. Then in the theta space, then we can try to do this is more or less like the zero order optimization to solve it here. But on the other hand, this problem, yes?
I'm a little confused. What is the P actually?
Oh, P is the real distribution of the data. Then that's the population one. We never know. Yeah, yeah. So here is
You just have like one fixed data set.
That's correct. Yeah. But in general, when we really do this, we need to do some data splitting. Yeah. So we use half of the data to do this optimization, intensively query this half of the data, then trying to find the best possible theta or a bunch of theta, and then use the remaining half to clean this whole thing, then select the best. Yeah, because that's more like the held out data idea. So just to make sure we don't suffer from the same adaptive data analysis problem. Yeah. So, But here, I mean, this is the one idea is we can use base optimization. But the other idea is, you see, if we only worry about the inner layer optimization, so here we could pose some prior distribution or prior policy for theta. Then for each individual theta, then we first can do this forward stuff, then the backward stuff, then to just get a W theta fit. And then we can use the forward stuff on the upper layer to evaluate what is the incurred loss. Yeah. So then we can just actually, once we have incurred loss and we have the policy pi theta that's parameterized, then we can directly use the policy gradient then to also search this in the theta space. Yeah. Then there are some more, I mean, the other algorithm, we can also use genetic the algorithms and then to solve it. So essentially, there are many ways to solve this problem. And if this W is differentiable with theta, then we can directly do stochastic gradient descent, actually, then to solve this problem. But in terms of simulational inference, what we care about is not just get the best point estimation. We also care about, I mean, for this theta, then the estimated theta, then can we do certain uncertainty quantification. So, or whether we can, using this formula, then based on the observed data we have to test a certain hypothesis, like properties of the underlying theta, so structure. So that's also within this framework. But that's not the major focus of today's talk, because in today we care about massive scale computation. So I want to explain a little bit more about, I mean, what is the computational infrastructure that can support this type of analysis. Yeah. Because you see here, obviously it involves several very complicated components here. So then it could be involved in deep reinforcement learning. So that's something already very complicated, and also involves the bi-level optimization, involve neural network. So there are a lot of parameters, and then the hyperparameters configurations need to be tuned. So then how can we develop some framework, I mean, then the infrastructure to support this computation? So then this where, I mean, the problem goes to massive computational experiments. Yeah. We want to do this type of computation, but the major difference between this type of computation and the more classical, I mean, the massive computational experiments, as I discussed with Warden earlier today, I mean, a lot of computation, I mean, in the classical scientific setting, they are just like the embarrassingly parallelizable. Yeah. So then you can use certain, I mean, the cluster infrastructure to do this. Yeah. But this type of computation, in general, it involves us to incur many CPUs and GPU to do the computation together, but these computational units need to keep interacting or communicating with each other. So that makes this computation paradigm dramatically more complicated. So then we want to study something newer. And also, I mean, because we are dealing with robots here, robots is different from the pure scientific, computational scientific study. It's a lot of robots, actually, the sensors and the actuators of the bots actually stay in the physical world. Yeah. So then when we are doing this type of experiments, sometimes we also need to get these things involved in. And sometimes they also involve very sophisticated simulators, like self-driving car stuff, and there are a lot of very complicated simulators got involved in. So then they also add extra complexity. So essentially, we want to develop some experiment management system that can simultaneously, I mean, organize all these different type of resources. Yeah. Like multiple computers, I mean, the cloud scale, there are many of them. And there involves many CPU and GPUs. How shall we do that? And then there are very heterogeneous storage. So there are different type of data, like some data from the sensor, like camera data. Some data are from the other database. Yeah. So then how can we get all these multiple storage, I mean, organized? And then and also there are different hardware bots and different simulators. Yeah. So this will motivate the second part of today's lecture. It's about the cloud system stack. So here is an overview of the system architecture I would like to explain. Because by the end of the day, we are doing the robotic related computational experiments. So there is some system called a robotic operating system that's directly deal with robots. Yeah. So then for the robot, it gives a very nice abstraction about different actuators, different sensors. You can use user-defined data formats. Everything is standardized. Yeah. But I will not, for today, not emphasize on this ROS stuff, this robotic stuff. And the reason is what we care about is the underlying the computational infrastructure. So instead of spending a lot of time on explaining what is robotic operating system, I will explain these 4 basic components here. They are Docker, Kubernetes, Istio, and DDS. So if, for example, your background is from computer science or from the industrial background, you will know Docker and Kubernetes has already become the current state of art in industrial applications. And this Istio is something newer. And then but right now it's becoming the dominating one. Then combined with Docker and the Kubernetes system, then they together called the DKI. So then this is the current state of art in industry. Here, one thing newer we added in, it's called DDS. It's a data distribution service. Actually, what makes the data distribution service special is later I will show you. This one very naturally connects to the robotic world. On the other hand, it is very compatible with the existing state-of-art Docker, Kubernetes, and Istio. So these things, there are several different terms. So they are not used separately. Supposedly, we should use them in a big full stack. So then essentially, Docker is the underlying foundation. We need to deploy Kubernetes over Docker. And then later, we need to deploy Istio over Kubernetes. And then DDS, then they are one after another got a full stack. But in today's talk, I will not talk about the super technical stuff. But instead, I want to focus on the logic. Especially, I want to just explain why we want this system to be together, why we want to adopt them. What's the underlying logic for that? And to understand this logic, we need to understand how these systems are dealing with many, many computers and many CPU, GPUs, so then many processes. So that's essentially something called a communication protocol. So then we need to understand that part a little bit better. But I will go to that part later. But first, I want to quickly remind you what is a Docker. But Docker is essentially the containerization system. But containerization, this is something the easiest to understand because in the real world, container, this is called a container. Container is a great invention because before the container time, if we have a bunch of goods like their rice or other stuff, we want to move these goods from one location to another location. That's a super difficult task because they are very irregular shape and they might contaminate with each other. But once we have the container, you see it's very nice structured stuff. Then we can put the goods inside and then close the door. Everything become, separated, isolated. So then that's the first thing. It's isolate things. And second thing is all the containers are super standardized. They're all the same shape. So then it's a very standard interface. It's easy to get them manipulated, organized. So that's a great idea. It dramatically help the real world. But then in the computer world, to implement this idea, that's the Docker system. It's open source software, created by the Docker company. It's just essentially we treat different applications, computer programs as the goods, and then their corresponding libraries as dependencies. Then we could just containerize them. So we can think about a container more or less like a light-weighted virtual machine. So then that's what Docker is doing. So this is all about Docker, because by the end of the day, we need to manage the many CPUs and many GPUs. So then how do we manage them? So then all these CPU, GPUs and all the programs, then we could think about this is we organize them in different virtual machine, lightweighted. That's a different container system. So Docker is the foundation of everything, but Docker doesn't worry about parallelization or everything. So then the Docker just containerizes things. But then if we have, yes?
Sorry, a slightly tangential question. It seems like such an obvious idea.
Yes.
Why it didn't happen a long time ago? The VMs were...
Yeah, actually, this idea happened quite a long time ago. So it's 20 years ago, Google already created this technique. And it's just Google did not open source this technique until 5 years ago. So then after the 5 years ago, after this technique become open sourced, and suddenly it become very popular. And then even though people have already had this idea.
I'm asking about containers. Like, why wasn't that done? Are you talking about containers?
Yes. Oh, you mean why is the?
Like the Docker thing, 15 years ago. Is there VMs were too fat, or what was the reason?
Oh yes. So virtual machine is something you virtualize or you use software to mimic hardware. Yeah. Container does not do that. It's much lightweighted. Yeah. So then the virtual machine is much, much slower. For example, let me give you a example. If you want to open a container, it's just like the couple of seconds. Yeah. But if you want to open a virtual machine, it could be like a minute. Yeah. So it's much, much slower. And a virtual machine costs a lot more resources compared to container.
So conceivably, the right answer to your question might be that people were doing some sort of pre-Docker by hand, in various applications. They did something that filled that same role just for and then it didn't seem to be clearly of a universal character, and so people just lived with hand-to-mouth version of this. So you would, telnet into some machine and copy in a bunch of things, and it was a kind of standard thing for these machines. You knew that it was going to work for those guys. For some other machines, you'd have another thing that you copied in. And I remember living through all of those years. And then people realized they could do something a little better, and then gradually someone had the insight that there was a product in it. So the prehistory of this is that people were doing a lot of the cloud stuff by hand and in an ugly way, but they were getting their work done. And then the revolution was, that we can package it and productize it and so on.
Yeah.
And then that has to be with the arrival of large-scale cloud services, where you imagine that there's a market for your ideas rather than it's just something you do yourself. Sorry, I
Yeah.
didn't.
Yeah, that's great. Thanks. And also, I think one more reason for why people care about this is people want to get things standardized. Because from the experiment perspective, then I conduct a lot of experiments, and I hope you can easily, reutilize what I did, and we can easily collaborate. So if everyone follows the same standard, then that makes things much easier. And Docker system nowadays has already become the industrial standard. Then everyone has already stick to it. So then they build the ecosystem, so it makes things even better. Okay, but you see the Docker is for each individual computer. Then we can put a lot of containers in. But then how can we get them connected so that they can interact with each other? So then that's where the Kubernetes system comes in. So this is a very important system component here. This is something called orchestral system, or just a management system. Yeah. So then we have many different physical computers. Each computer have different containers. Then but we want to utilize all of them together. Yeah. So then how shall we do that? That's Kubernetes. Yeah. Kubernetes was created by Google, and then got open sourced 5 years ago. And then nowadays it's already become a standard, it's dominating role. But here, I want to introduce you a little bit more about a high-level idea of this Kubernetes system. Assuming this is the user, this is us, we want to conduct some computational experiments here. So then what we are going to do is this Kubernetes system uses still the very popular master worker, the model. Yeah. So there is the master node. Think about this is one computer. We install this master node there. And on this computer, there is an APS server. It's a process always alive, listening to the request. Then we could give our request, the config in certain language, like a YAML language, then give it to the APS server. then the master node will be able to configure, a lot of different worker nodes. Yeah. Then the worker nodes, each worker node contains many containers. Yeah. So then this is more like the brain of everything, and then the other one are just workers. Yeah. So this is the high-level overview of this Kubernetes system. Yeah. So you see everything is in the cloud. Yeah. And one master node could simultaneously manipulate like tens or hundreds of worker nodes. Yeah. So each worker node is more like a computer. So everything is connected. But here, there are many terminologies. But one thing I particularly want you to pay attention is this thing called a proxy. Proxy. Later, this proxy, or later I should call that a kube proxy, Kubernetes proxy. Will be something super important. It helps us to understand how the different, the Kubernetes worker, they are supposedly to communicate with each other. It's along this line of thinking. Then we can start from the Kubernetes, motivates why we want EC2, and then why we want DDS. So then this is a proxy is something important. Okay, but before I introduce you this Kubernetes proxy, I want to introduce you one more concept, a very important concept. It's called pod. Pod. Because you see, this Kubernetes system is organizing many different nodes. From now on, whenever I say node, you just think about node as a physical computer is fine. It's a computer. It could be physical, could be virtual, but let's just think about this physical. So then, but how these containers are being organized? So the smallest, the manipulation unit, organized by Kubernetes is something called pod. So pod is more like the container of containers. So we want to organize a bunch of containers together. Then these containers, in general, they have some intrinsic logic structure. Or they don't have to. So then, but they organize them into different pods. So then the pods will be something that the Kubernetes really care about, directly manipulate. And then with the pod, sometimes if certain nodes, certain physical computer, got crashed, then the Kubernetes, the master could know that this node got crashed, and then it could just move this pod on this node to the other node, like this pod C now from node 2 to node 3 if the node 2 was died. So this is the concept of pod. And the pod must be contained in one single node. We don't allow one pod to be across node. This is just for you to know. So then once we have this definition of pod, then how could Kubernetes, the different pods, they could interact with each other or interoperate or communicate with each other. So this is related to this concept called proxy. So in Kubernetes, this proxy is called a kube proxy. Later I will show you more detail. But before that, I just want to explain to you a little bit more about this idea on proxy. Because this is the idea the concept we use every day. Like whenever we are dealing with a computer, we always have some proxy. But what on earth is that? So, in the computer world, everything, let's call that an entity. Could be different process or something. Then sometimes, the entity A wants to communicate with entity B. Like I want to open a certain website. I can directly, A can directly communicate with B and then ask B to do something. But proxy is more or less like a middleman in the middle. Then when A wants to request something from B, instead of directly talk to B, talk to the proxy first, and then proxy talk to B. So at the very beginning, this sounds like a weird idea. Why we want to do that? But there are many reasons here. So actually, by doing this middleman, then the proxy, for example, it can block the certain information. So this is related to security. So then sometimes A might be malicious process, and then we want this proxy to help to guard against A from B. So then that's one way called block. And second thing is from data analysis way, because all the communication passes through this proxy, so then the proxy can be an observer or data collector. We can collect a lot of information, do data analysis to improve the system performance. That's also super helpful. And this proxy can also do this rate limit here. So then sometimes, we don't want a certain A and B utilize all the communication bandwidth. It can help to optimize this whole thing a little bit. And then the proxy can also do the load balancer, to make the whole system work better. So there are just, by adding this proxy, it has a lot of advantages. And later, we will see all these distributed systems, actually the key or their soul is about the proxy. They use different type of proxy and then to be able to, organize it together. Okay.
Is there a way to quantify the performance hit of having a proxy?
Yes, there are. So later I will explain that. There are something called QoS, quantity of service, that's related to this. But now we have known what is the general concept of proxy. Now let's go back to the Kubernetes system. Kubernetes is just an organizer of different Dockers, of containers. So then you see here, we have a specific concrete example. We have 3 different computers, node 1, 2, 3. And then for each computer, we have this thing. This is called a physical IP, or we call node IP. Let's assume they're the real IP. They are the address of this computer, so that later if we want to access this computer, we can use this number to find where is it. So this is called a node IP. But then within this, each node, there are certain pods. So as I have explained, pod is the basic units that Kubernetes organizing the different containers. So then you see that each container has another IP. This one is called cluster IP. This is more like an internal one. Internal IP is just like we have a big building. Building has an address. That's the physical one. That's the real one, because when people want to send a message to us, they need this. But internal IP is more like within the building. We gave the different room different names, like the room A, room B, room C. So then this is the internal one. So then from outsiders, people don't look at that. So there are 2 types of IP. But then if different pods want to communicate with each other, so then this is assuming we are doing large-scale computation. Then the different processes on different nodes and different pods, if they want to communicate with each other, like they jointly calculate some gradient or just do whatever the data transfer, then they will just communicate through this process called a kube proxy. Kube proxy is more like a process. It's running on all the computers. But then assuming we have one pod A want to talk with the pod B, so then they could just do this through the kube proxy. So talk to kube proxy saying I want to find B, and the kube proxy will just deliver this information to B. And for this step to be able to done, because everything is within this Kubernetes system, we don't need this real physical IP. We only need these 2 virtual IP. It's good enough. Just like in the building, I want to, from this room, find another room, and we don't need to know what is the building address. So then this is the within node communication. But then what if we want to, across the node, like from the port A, we want to talk to the port in node 3. So then this one, we just follow the same step, just using the kube proxy. Because kube proxy across all the different nodes, it has the information from everyone. So then if you want to go here, then this is just like from stats building to the math building, then the 2 different rooms. Then we can also just easily do this, because this is all within the same university, the same system. So we don't need to know this abstract address. But sometimes, a lot of applications, we may have some external request here. External one. So they are like, they're not inside Stanford University. Then the people wants to communicate, how shall we do that? So for example, this is port C in the node 2, and there are some requests from outside saying, I want to access the port C. How can I do that? So to do this, then this is another important concept from Kubernetes. It needs to create something called a service. Service or microservice. So then the service is more serve as a interface for this port C. But then by service, you see here, there is it utilizes the physical IP of this second node and with a port that's called the node port. So then this is supposedly the outsider people could utilize this address to find this service, and the service uses the internal address then to find the corresponding port. So then with this mechanism, the external person can also utilize the kube proxy to be able to access the internal node of this Kubernetes system. So basically, this is everything about the Kubernetes, the proxy, how everything is being organized. So, and this one is also called a microservice structure, because nowadays, when people are doing large-scale computation or large-scale, the cloud application, then what people care about is that they want to make this whole thing, instead of write a super big program that's called a monolithic program, then they want to decompose this whole thing to be small units, as small as possible. Then you will see something like this. So each node here corresponds to a service, as I just explained in the previous page. Then this is called a microservice structure. So there are a lot of very complicated dependency structure here. But the reason people want to do this is it isolates different, the computation units as much as possible, decouple things. Yeah. So that's the benefit. Because if one thing got wrong, if you want to change one thing, just change your stuff. If you don't change the interface, it's make the whole maintenance of this whole system very easy. So that's microservice is a major trend nowadays in the IT industry. Then the people are doing this. Yeah. But you see, on one hand, it's good because it's isolated things. Yeah. But on the other hand, this whole thing is very decentralized. And then debugging the program is very complicated. Sometimes, if I have a parallel computation program and there are a lot of complicated, the dependency structure, then after I run the program, there is a bug. Then how can I find this bug? Then in such a tricky, complicated things, it makes things very difficult. Then to solve this problem, then one very simple idea is then the people have is why not let's centralize all these informations. Into one single control panel. Yeah. So still underlying, all these things, they are organized, the services are still distributed, but all their information are being centralized together. This is another concept called service mesh. And actually, Istio is one type of software implemented this service mesh. So you see, Istio solves one problem of the Kubernetes, is how to debug a very distributed program. Yeah. So that's the motivation of Istio. But let me give you a little bit, the more explanation of how Istio implemented this service mesh idea. So for Istio to work, it actually utilizes a existing mechanism from Kubernetes. That's called a sidecar mechanism. So what is sidecar? So because Kubernetes just create different pods. That's the basic units. So sidecar mechanism is just saying when Kubernetes create a new pod, it should automatically create another container. It's called sidecar. Sidecar is just more like a secretary process. For each pod. Each pod has a secretary. So then with this secretary, you see that there are two of them. One is the original service. That's another container. This is a sidecar. Then if we look back at this whole, the microservice structure, then each individual pod, there is a secretary. So that's this in Istio is called the Istio Envoy. So it's a sidecar process. Yeah. So then each sidecar is more or less like a secretary allocated in each individual distributed unit of this computation. Now, Istio is more like the head of all the secretary. So then everyone reports to Istio. So then from the Istio perspective, it can collect all the information of everyone. And then it can also send the information to control the communication of all the different pods. Yeah. Because once this sidecar is given there, all the communication just all through this sidecar. But of course, the sidecar will call the kube proxy, then the communication mechanism from Kubernetes to continue to do this. Yeah. So this is called the Istio idea. So it's very simple, but then it's quite effective, especially in the past 2 years, then the Istio becomes super popular. So it's really promoted by IBM and by the Google and the Lyft. Yeah. So they are giving this idea, developing this as an open source project. So once we have the Istio, so now let me show you a little bit more about what we have already covered. So we explained what is a container. That's essentially the Docker system. And then we explained what is Kubernetes. That's essentially the pod stuff that organize all the containers. And there is a kube proxy so that different containers could interact with each other. And then, but because there are so many possible, the pods, then the whole thing structure could be very complicated. Then within each pod, then the Istio just insert a sidecar container. So that's Istio. So then the Istio communication will through the kube proxy. So then you see this is currently we have explained. But the problem is all these communication, they are only within the Kubernetes system. So you see this, I put the word internal. Everything is still internal the Kubernetes system. But this may not be enough for many applications. Let me give you an example. So in certain applications, we have external device. For example, in robot applications, yeah, robot may have the cameras, and then there are some other the video surveillance stuff. Then they are in the physical world. Actually, they have very weak computation power. They are not inside this Kubernetes system. They are not on the cloud. Actually, this is called edge. Yeah. They are on the edge. Yeah. So then, but we need them to be able to communicate with the process we have, yeah, internally. Yeah. So that's one thing. Yeah. And another thing is, even within this Kubernetes system, as I explained before, Kubernetes, the basic computation units, the units that Kubernetes manipulate on the communication side is a pod. But there are many, many different containers inside. What if we want to characterize different containers so that we know we want to say this one, cannot access this one, and we want to separate people different group or something? Now we don't have the more refined control at this level. Yeah. And to solve these two problems, that's where the DDS shows up. Yeah. That's DDS. Yeah. So this is the motivation why we want to do DDS, because if you want to do the robotic type of application, then you want to talk to outsiders. And on the other hand, for a lot of computations, we want to have more refined control of the containers units. then we need more refined the fine granularity control. Then that's DDS. It's useful. But DDS, the full name is Data Distribution Service. Let me give you a little bit of rough idea about what's this. So DDS is something very refined, I would say. It's not just a container level. In the whole computation, whatever things, if they can install the DDS client. DDS client is a very small program. Now just if you have like a 200K space, you can install that. Then once you install that, DDS is just like everyone has a cell phone. Then they are able to communicate with each other. So then once this one, I call everyone install a DDS client is called an entity. It could be a container, could be a process, and could be something even smaller. So then with this DDS entity, the first thing we can do is we could characterize people into different domains. So then this domain, just like in program, is called a namespace. Yeah. And then only the entity within the same domain, they can communicate with each other. Outside my domain, you cannot talk. Yeah. So this type of access control is very important, especially for robotic application, because sometimes, each individual entity could be one actuator of the robots, and then the eye of the robots, and all these things. You don't want the other robots to confuse with each other. So we need this type of domain control. But then once we have the domain, if we focus on all the entity in the single domain. So first, I want to remind you, this is a node 1, 2. There are several different nodes. You see that the entities within the same domain could be across the very different nodes, computational nodes. And then but for all the entity, within the same domain, they are using this topic model to communicate with each other. So first there are they creatively, they use some distributed, the file system to build something called a global data space. So then all the entities, they can either be a writer or reader. They can subscribe this topic. So like one topic is like the vision system of the robots. So then it's just this reader is like a camera. It reads in the data and then store the data in this cloud. Then the writer, will just access this information. So you can subscribe this. And then the one camera reading the data could be many different people subscribe. And one thing here is DDS supports this QoS service. QoS means quality of service. So then it depends on whether you want this, to be very high quality, the communication or low quality communication. Everything is controllable here. So that's called QoS.
So
yeah.
What I can imagine is I need in this process running, on who knows what node, in which thread, etc. Needs some data that's produced somewhere else that
yes.
is completely not transparent to me. Like I have no idea what's going to be running
Yeah.
So it gives me some way to refer to some data that's going to be produced somewhere else. I don't know where.
Yes.
Is that what this is solving? Or is it
Yeah.
different?
Yeah, this type of infrastructure actually will support the type of system you mentioned. This is the basic underlying infrastructure. So build upon this, we could add one more logic layer. Then that logic layer, I mean, from the end user perspective, everything will become transparent. They don't need to see all these things, but that's because the person who built the experiment management system utilizing this to program everything. It's a smart program, then it must be do everything automatically. For example, in the future, when we are trying to do a type of experiment, like XYZ experiment, so all what we need is to specify, I need this type of data, this set of data, that set of model, and with a certain set of model configuration. I want to run the full loop, then run everything. Then that's all the end user needs to specify. But end user doesn't need to worry about where the data stores, which model. I mean, the model have different version, which version, I mean, the stores where. So because underlyingly, everything will be, I mean, handled by this type of stuff. So in the middle, people who implemented the experiment management system needs to worry about all these things. But once this is done, the end user doesn't need to care about this anymore. So, but then here you see that it has very refined granularity. So this is like you care about a certain quantity, like a certain computation. I must get a super high quality data. Then we use a high QoS. Then you cost some more resource.
So it's part of QoS simultaneity that I have different processes that have to be in sync as they run. That there's some physical time that they have to be producing.
Yes, actually QoS is related to this. QoS, you can think this is more like, because by the end of the day, data needs to communicate from one computer to another computer. So there are different communication protocol. One thing is called TCP communication protocol. Another one is called UDP. TCP is more like I communicate to you and you need to give me feedback, and then I need to feedback again, then do back and forth. But then the reason is that this one can secure I deliver the information to you I want to deliver. But UDP is just I send you the information, then I don't worry about anything. So you see there is definitely trade-off. Like TCP is more secure, high quality, but it's much slower. And then the UDP is much faster. So QoS is more like you specify what you want, and then it will try to balance between things and get the best, the result delivered. So, but this is the DDS stuff. And then DDS model is something called a publisher and subscriber model, because we have a topic, you can publish a topic, and people can subscribe this topic. That's the communication model. Okay, now I finished basically all of them. I just want to give you a recap of what we just explained there. So I first introduced Docker, but Docker is not important. Just think about that as the virtual machine. It makes things isolated and standardized. But build upon Docker, to organize things, we first have Kubernetes. But Kubernetes is pretty nice, but it's more refined at the pod level, and it's very decentralized. So maintaining them is not easy. And then to solve this problem, that's where we introduce Istio. So Istio is just centralize all the microservices in one place. It didn't eliminate the complexity, intrinsic communication complexity, just centralize everything together so that in one place you can manipulate and observe and manage all of them. That's Istio. But the problem of Kubernetes and Istio, they are still internal world. Internal what? Internal to the Kubernetes system. What if we want to handle the external world? That's like the cameras or the IoT device. That's the DDS comes in. And what if we want to get the more refined control? That's DDS comes in. So basically, this is a nested structure of these different communication protocols. Then the Istio nested in the Kubernetes, DDS nested in there. Yes?
So every data generating, let's say, device or whatever, has somehow got to register with your DDS, right?
That's correct. Yeah, it must register and register through that topic model. Yeah, so then that global data space. Yeah.
So for example, then you have predefined namespaces or
That one doesn't need to be. Yeah, that one doesn't need to be predefined, because when someone got alive, then it could just you can just adaptively define a namespace and put it there. Then everyone can use that to communicate with each other. Okay, so these are all the these.
Last question. So
Yeah,
which means
please.
that You're not trying to organize that in any structure. It could be one huge bag of namespaces.
That is correct, yeah. Then it's a huge stuff, yeah. Because all these things are basic, essential foundation. But then we need to build upon this to add the logic layer Dave just mentioned. And actually, that's what we have already done. In our team, we have built the system, or the core of the system, named Magix OS. Yeah. OS means operating system. Magix is my last name. So you see, this system actually exactly, the organizing all the computation in the Kubernetes world. But here, you see, whatever it is, it's algorithm, or it's sensors, or simulators, or even the hardware stuff. Then by the end, it's everything is containerized. So then they are just containers. And between all these containers, their communication protocol is publisher and subscriber, the model, yeah. So because they are mainly using the DDS, yeah. And then for the operating system to manipulate all these different containers, this is a service mode, yeah. So this is more like we use the Kubernetes master to control everyone. So this is the infrastructure of the underlying the EMS system called Magix OS. Yeah. And then the multiple users could just access this system, then do computations in this underlying stuff.
Publisher and subscriber is basically how ROS works, right?
That's exactly correct. But that's essentially the ROS tool. Yeah, because what Warden said, the ROS is a robotic operating system. Robotic operating system, ROS, has two versions. One is version 1, another version 2. Version 1 is more like Python 2, and version 2 is more like Python 3. So the same situation. Version 1 has already been, no longer be supported, but still it's popular. But then version 2 is the future, and actually what we are working on is version 2, the ROS 2. Okay. Then with this Magix OS, that's essentially the kernel of the system. But built upon this Magix OS, this is one of our ongoing projects. What we are doing is developing one thing called a robotic experiment management platform. So that's also called Magix Kate. So then build upon the cluster we have. Then we are trying to just make this whole thing to be a real EMS system. For this system, when people want to run the XYZ experiments, when people want to run the deep reinforcement learning, they don't need to worry about all these underlying stuff. Yeah. All what they need is just to specify certain things, and then everything will be handled transparently. Yeah. But this is still the ongoing project. Yeah. So that's what we are working on right now. Yeah. Okay, so that's the second part. So then for the third part, because we have already developed the Magix OS, the core of the system, I want to just use two examples, pilot study on robotics to illustrate, what have we done, utilizing this system we developed. So the first application is a collision-free navigation problem for robots here. But for collision-free navigation, essentially, we have a robot. This is the starting point. We want to from starting point to the ending point here. So, but in the middle, there could be human got involved in, and humans' behavior may not that easy to be predicted. So then, how shall we solve this problem? So then, one very popular formulation is we can formulate this whole thing as a Markov game, with the robot as the protagonist agent here. One player, and each individual person as an adversarial agent here. So it's a multi-agent game, and each agent has its own, the utility. It could be zero sum, could be general sum. Yeah. But this is called a Markov game. Then everyone want to just solve this game. Then by the end, the robot has its own strategy. To finish the navigation task. Of course, we hope it's the collision free. Yeah. But because the human got involved in, you see, it's very hard for us to model human. So then instead what we are doing is we do this adversarial setting to train the robot simulator. Adversarial means, because it's very hard to model human, then we assume you are even malicious, somehow. So then we have different simulator models about a human process. Each human is modeled as a Markov process, but then you see there are certain strategies. Sometimes this is called a chasing strategy. Different humans, they are chase these robots. Robots from starting point to the end point, and humans are chasing the robots. Sometimes it's called crossing. Humans want to from here to here, but the robot, but the humans could be just like to walk towards the robot. That's purposely. Or another strategy is blocking strategy. So they correspond to different type of simulators we have. So they are definitely oversimplified, but they are just simulators and the robots trying to understand the real human behavior. Then under this model, then how shall we train the robots here? So we are using this path following strategy. So this one in optimization is more like an interior point method or parametric simplex method. We want to start from something from simple to complicated. And in machine learning, people call this curriculum learning stuff, but it's essentially the same idea. So in the Markov game setting, what we did is at the very beginning, we modeled the human very benign, in a very benign way. So you see, robots try to go from here to here, but then the humans, they are just chatting with each other without moving too much. It's pretty easy for us to use the reinforcement learning algorithm, like a PPO algorithm we are using, to train this scenario well. And then once we get the policy from this scenario, we use that policy as the initialization for the next setting. And here, the human become a little bit more complicated than they are starting to walk towards the robots on purpose. So then but they don't walk very fast, so it's still easy to handle. So then after we get the policy here, we can move to the next setting. Here, the human become even more malicious. So you see they are starting to run, and someone is strategically block the robot here. But then we continue to train this whole thing. And then by doing this, we get the full regularization pass. So then once we get this pass, then we can just also do the empirical calibration. So then because we can let the real humans come here and we interact with the bots. Then to see for different, the different simulator, because under different simulators, there are different policies, and then to see which one works the best, then do the adaptation. So by utilizing this algorithm, we have developed the trained strategy to the physical bots. This is a Turtle 3 bot. It's more like an experiment bot, but full-fledged, and it works very well. In this setup here. And then from the system perspective, we are utilizing this MagicOS system, then containerize all these reinforcement learning algorithms and containerize all the simulators. So there are many simulators could be simultaneously launched, and then to collect the data. And then after they collect the data, then we can use the reinforcement learning algorithm, then distributedly to do the computation. So once everything has been computed, then the trained policy can be deployed to another, containerized ROS system, robotic operating system, then to control the physical robots here. So that's how this whole thing form a whole closed loop. And through the physical robots, external data like a human interaction with robots can also come into this system. Yeah. So that's the whole thing. We view this as a larger, experiment. The robotic experiment. Yes, please.
So for this whole process, are you looking at the results interim before you run this whole experiment, or you just run all?
You mean we first, in this setting, we first run all of them and store them, then they interact with the human, yeah. So because we want to make this whole thing as automatic as possible, yeah. So then and also this is not a super complicated setting because all the simulators are indexed by some low-dimensional parameters, so we are affordable to run all of them. Yeah. So then we use 80 GPUs and to run this whole thing. Yeah. There are 1,000 CPU cores. Yeah. Okay, so then right now, currently what we are doing is we are deploying the same algorithm onto this much bigger bot. This is called Badger bot. It's created by the the JBL. So then this is something called a retail robots. It's being deployed in the retail store and actually interacting with people. Then we want to test its performance. This is an ongoing work right now. Yeah. Okay. So that's the one study on the robotic motion, the navigation problem. And we did another problem. It's jointly with the people from Georgia Tech. It's on high-dimensional motion planning of robots. But motion planning, it's essentially like this is the robots, and then it just manipulates certain objects with also possible human getting involved in. So, but for this type of problem, so first, what's the difference between this problem with navigation problem is, it in general, the dimensionality is high. So what does it mean? Because here, this is a workspace view. This is just a two-dimensional maze, and this is a very simplified robot. You see, this robot has one point and then the one arm. So there are only 3 degree freedom because the XYZ has 2 degree freedom, the location of the robot, and also there is an angle of this arm, that's the 3rd degree freedom. But then for the motion planning, what we care about is we have a starting point, starting configuration, and then we want to move it to the ending configuration. But all these things need to be happen in the configuration space. In this setting, the robot has 3 degree freedom. We see this is the configuration space. It's 3 dimensions. This is X and Y, that's theta. Then this is the feasibility space. So you see, even for this very simple problem with very low degree freedom robots, then this one is already becoming very complicated. But in the real world, robots could have like the 10 degree freedom or 30 degree freedom. And then it's much more complicated than this. So this is called the challenge in high dimensions. But to solve this problem, actually existing literature has already had a family of very powerful algorithm named the tree-based sampling algorithm. So their strategy is pretty simple. This is state of art. So assuming for the robot, we have the starting configuration, that's called a start, and this is the end configuration with possible, the block or the obstacle in the middle. Then how are we going to finish, find the right configuration? This algorithm is very simple. First, we uniformly sample a point in this space, and then check whether the connection between this start point and this the point we sampled, there is any collection or not. And if there's no collection, then we use a stamp size, then to actually walk toward that direction for certain stamp size, the max you can do. Then generate one tree. So then whenever we have a tree, then we keep doing this whole thing. Then generate new points, and then do collision checking and decide which node we want to connect to this tree. So then that's the simple algorithm. Basically, we grow a tree. And this algorithm called TSA, it has the guaranteed, the optimality property. But this is the state of art, but it's not good enough. The reason is, first, in terms of sample, it's not really efficient, sample complexity. The reason is we always use uniform samples, and then a lot of samples got to collide with the obstacle because the sampling doesn't consider the possible structure topology of the obstacle at all. So a lot of them got to collide. And also, sometimes, like in this situation, this is the starting point, and we want to go to this ending point. So there are some easy way to go there, but because there are a lot of white open space here, then a lot of samples are wasted on the open space. So basically, it's not very efficient in terms of sample complexity. And also, the bigger drawback is, for some applications, actually, there are certain global patterns. Like if this is starting point, this is end point, and another instance, this is starting point, this is end point. We see there is always a way we should go this way and this way. This is global patterns, then they're pretty easy for human to find. But using this tree-based algorithm, it's not very easy to discover this type of global pattern. And also, certain situations, there are local structures, like here. If starting point here, and then we see within these 2 red rectangle, and then this local structure is very similar, but definitely, this algorithm cannot capture these type of things. So then all these limitations of the state of art, that motivates us to think about learning-based method. But what shall we learn? Why we want to learn things? So the main motivation is, even though this robot in the configuration space is high-dimensional configuration, but for the real operations, in a lot of situations, the robot trajectory lies in some low-dimensional manifold, but it's just this manifold is very hard to describe. Then that's where if we have a lot of samples, from certain simulators, that's where we might be able to capture certain manifold structure. That's the motivation of learning-based algorithm. But the algorithm itself is not complicated. essentially, I mean, this is just like if you're familiar with Monte Carlo tree search, then like the same AlphaGo stuff, then this is just the same type of algorithm, but continuous version. We want to learn a value function and a policy function. So then when we are growing a tree, value function just tell us which node of the tree we want to grow. That's called as parent. Then based on the value, value is which node if we grow, then that can give us the maximum gain. And the policy function is just based on the current node to grow, then we want to sample, where to sample. So then here, this U is the problem configuration parameter. So essentially, it's where the initial and the goal and the map of the whole thing, the problem. So then if we can get these two functions learned, then that'd be great. So how shall we learn them? So this is called imitation learning. But essentially, this is the same idea as the simulation neuralization. So we need a simulator. Simulators to just simulate what is the possible problem configuration. And then simulate the map, simulate the initial and ending points. Then once you simulate things, we can generate a lot of trajectories. Okay, sounds good. So then all what we need is to just fit. I mean, if we from one point to the next point, then we just fit this policy function, fit it well, and then fit the value function. So then just get everything fitted. So then we can learn this value and policy functions. So once we have this, then there are some other problems because this is a biased sampling. Then sometimes it might be got trapped by certain local points. But to solve this problem, we can use a certain like a UCB, upper confidence bound type of exploration strategy to make it escape the gap. So that's just some minor twist. But this whole algorithm is called the next algorithm. So then it involves a lot of heavy sampling, and it also involves a lot of neuralization, the neural network training. So then it's also the type of applications benefited by our architecture, the computation architecture. So then we train this algorithm and then evaluate the performance. It works very well. Then this is in the simple setting. Then the traditional algorithm, the best state of art is RRT algorithm. Our method is much better. But then we also deploy this on the robots. Then here, this is robots from the shelf. I mean, they're trying to move from one cell to another cell. So then we simulate the different shelf structure and then the different initial and ending configuration. Then this algorithm is much faster than the classical, I mean, the planning algorithm. So this is the planning part. So then I basically covered all the things I want to cover. And then the last part is the same idea can also be extended to the more general setting in AI, like the optical character recognition and object recognition, or even the dialogue systems. So then there are a lot of the extension of this whole thing. Okay, so here's the summary to this talk. So I first introduced a generic framework that's named the simulational inference framework. And then we spend most of the time on talking about this underlying cloud infrastructure that supports this type of framework. I mean, how shall we do the computation, how different things can organize together. Then the illustrated tool, I mean, the applications for that. Okay, I'm done with that. Thanks a lot. Yes, please.
So, in terms of the computational framework, there's also this Lambda framework that Amazon has, right, where you can actually compute Lambda functions at very low cost and so on. Is there any connection, any comparison or any?
Yeah, I think there are some comparisons. Yeah. So first, this type of things they are useful for the robotic related computation because of the explicit emphasis on the DDS data distribution service. Yeah. But this is the type of thing, the Lambda framework, I don't think they can do this. Yeah. And also this type of things, in some sense, they are more efficient on utilizing your underlying infrastructure because Amazon stuff is, because Amazon as a cloud computing vendor, underlying service, a lot of them are still utilizing the virtual machine. Yeah. So then that's because Amazon has huge amounts of hardware computing. I mean the computation hardware. So then they are affordable to do this very heavy lifting, the virtual machine. But here, I mean, the computational researcher, what we care about is fully utilize the resource you have. So then this type of structure is much more effective at fully harness what you have. Yeah, that's the quick answer for that.
So what infrastructure are you writing this on? Is this on Azure or some local cluster?
Yeah, that's a very good point. So far, what we have done is running on 15 the physical computer. So then that has 80 GPUs and 1,000 CPU cores. But the same platform is actually trivially migratable to the public cloud vendors. Like we can migrate this to the Google GCP, to Microsoft Azure, or even to the Amazon AWS. But to migrate this, we need the public vendor. I mean, they're each individual virtual computer. They should be able to deploy Docker system. Whichever computer system, the cloud system, if they can install Docker, all these things are migratable there. So that's
saying, so Docker's limitation because you've got root capabilities whenever you run Docker.
That's actually, first, I mean, it's correct. Docker is the limitation. So, I mean, whichever we want to migrate to, they must support Docker. If they don't, then there's no way for all the upper stuff, I mean, to be going there. So the reason is Kubernetes is really manipulated Docker stuff, the container stuff, and everything is built upon the Kubernetes thing. Yeah. So then if, for example, a cloud vendor saying that I don't support Docker, then we screwed. But actually, all the cloud nowadays support Docker. So there's no trouble for that. Yeah.
So, please.
Yes.
I had a question about Istio.
Istio, yeah.
Istio, go over again the purpose of it, because I was a bit confused. It seemed like it deployed a container within a container. It helps in debugging or managing microservices.
Yeah, actually, the Istio, I want to just reemphasize the motivation of Istio. Istio is just first the whole system. Without Istio, it's perfectly workable. Yeah. So then they use the Kubernetes, then everything is working without Istio. But what Istio buys us is just this is a decentralized system, and you are managing a lot of dependency structure, communication structures over many different nodes and pods. Yeah. It's very complicated. Yeah. What Istio did is Istio just add in utilizing that sidecar mechanism so that they can collect the information and then into a central place and use this central panel to control everyone, control their communication. That's all what Istio did. Yeah. Nothing more than that. Yeah. So yeah.
Is like a clone of the Docker image?
Yeah, sidecar is actually a container because this is a pod and a pod hosts a container, and each container, sidecar container is very simple. It only has one process. This process is communication process. They don't worry about anything else. Yeah. So then just like a sex tree being injected into this specific, each individual pod being created. Yeah. Then we can centralize, manage everything. Yeah. Yes, please.
Two questions. I guess the first one is, does it make sense, or is there any way for the proxy to be self-contained to each container rather than as an overall layer?
Yeah.
Maybe that leads to even greater extensibility.
So your question is whether these proxy, I guess you mean kube proxy, to be contained in each individual container.
Just kind of like software objects.
And then whether that makes sense or not. Yeah, so I do not think that makes a lot of sense. Yeah. Because the kube proxy, the main purpose is trying to get all the different pods across different nodes connected. Yeah. So this one cannot be completely isolated in one single container because otherwise he doesn't know what's happening in the other places, who dies, who created, who got alive. And then it must be, stand out, and then across all the container, all the pods. Then it can serve its functionality. Yeah.
How about in terms of security or load balancing of those two things? Why can't it be self-contained each thing?
Yeah, actually, you mentioned this load balancing stuff. Actually, that is the purpose of kube proxy. It also, when they are doing this delegation, it also do the load balancing. But security part, you are right. I mean, that one doesn't do super well. But that's another purpose of Istio. Once you deploy Istio, then you have another chance. Sidecar, I mean, manage all the communications, and then whatever security rule, you can program them into using Istio into the system. Then you get the security part.
And my second question was, from here, where is the kind of progress? I guess another way to phrase that is if you're giving the same talk a year and a half from now, how do you think things will look different?
I think so far this talk is pretty advanced, and it's advanced in the sense that because I'm covering not just the current state of art. I mean, let me explain to you the state of art. State of art is Docker is standard, Kubernetes is standard, Docker, Kubernetes, they dominate here, so this is for sure. And Istio is like 90% dominate. I mean, then basically people are sure very soon Istio and these three will be the dominating one. DDS is something newer. Then nobody, I mean, has actually utilized DDS this way yet, and we are actually doing this for the first time. So I hope after 1 year or 2 years, this talk doesn't change. That means the DDS really becomes something standardized. But otherwise, I mean, if, for example, people don't adopt DDS, they may use some other things to do that more refined control. That will change the story a bit. But at least I'm confident for the robot stuff, because DDS is the official communication protocol supported by the ROS. So that means at least in robots, if you care about that, DDS must be there. So that, but for the more general computation, DDS serves the purpose, but not sure whether that must be the standard.
So you don't necessarily have ideas that you think 4 years from now would layer on top of this? Because that's sufficient.
4 years from now on, I think all what I can sure is the whole logic is still the same. But it's all these softwares, like whether people still use Docker or Kubernetes, it's not super clear, because I'm pretty sure people will still follow the same logic about different protocols, one nested another one, and build its whole thing, organize everything. This one is invariant, but all these softwares could be easily changeable. So then depending on, like for example, if IBM open source a super powerful one, then the people may suddenly in one night just like replace certain parts of this architecture. That's possible. Yeah, but I think this structure and the logic is something what do we care about, and then it's this logic, this infrastructure, actually the whole thing together supports us to build a more powerful EMS system. Yeah.
Do you care?
Yes.
So I know you as someone who's worked on traditional statistical topics as
Yeah.
well, and this is
Yeah.
quite different.
Yeah.
Do you care to comment on the change in career orientation?
Yeah,
that would
that's
allow
right
you to
here.
Span from stats articles to the talk you've just given us.
Yeah, I mean, this is not a very easy transit. I mean, basically, I mean, in the past 2 years, I mean, I have been studying this, and for the whole team, we did not publish papers actually. So then it's just this starting from this quarter, and we just published the first 2 papers on this. But then I think it is some transition. But the problem is, I firmly believe, I mean, nowadays this whole field is transitioning from the pure theoretical, I mean, to the somehow computational. And especially, I mean, the robots, I mean, that's something, I mean, later will become important here. But this is where I found it's not a lot of effort has been heavily invested on. So that's like especially the robotic experimental management system. And that's because it's painful. So there isn't so much work has been put in. So that's where we hope we could make some contributions. Yeah. Right. This is not easy. Yeah.
Okay, well, let's thank our speaker again.
Okay. Thanks a lot.